Jason Blocklove is an adjunct PhD faculty member in the Electrical and Computer Engineering Department of New York University. He previously worked at Johns Hopkins University in the Applied Physics Lab on digital hardware and embedded system design. His research focuses on additive manufacturing security, leveraging generative AI models for hardware design, and security analysis of AI models for generating hardware. Jason, welcome, and it's all yours.
Thank you very much. Excuse me. So thank you very much for that introduction. I'll be talking about automating hardware design with large language models. Uh, it's worth pointing out to start that I'll be discussing automating digital hardware design with large language models. Uh, we've been looking a little bit at the analog side of things, but very much not the focus of this. So I'm sorry if anyone's disappointed off the bat. So when we discuss digital hardware design, usually we're talking about something like what I've got on this slide here, the digital design pipeline. We're starting with this initial system specification in plain language. You get someone coming to you saying, I need you to design me a filter with these caps for this application, or I need you to design an AXI peripheral with, this specification using AXI Force Stream or something like that. You start with plain language specifications, and then ultimately it goes to someone who can architect the design, and then someone to actually write the Verilog, maybe the same person, maybe not. And you get the functional design, and then that gets synthesized into the circuit and the physical design. And throughout this entire process, especially when we talk about something like making an ASIC or an actual, taping out an IC, this is a difficult chain with a lot of different steps in it, and oftentimes a lot of different people in it. So the real question that comes up here is, well, how do we simplify it with technology that we now have access to? Back in really 2020 and through 2021 and continuing through now, large language models have been very much on the rise when it comes to things like writing code and now writing hardware. It started with what we tend to refer to as these auto-completion models. It's things like your GitHub Copilot, where you'd start typing something and it would just suggest how it wants to finish the phrase, or you'd start typing a function definition, it would just tell you how it wants to finish the function, et cetera, et cetera. And these models are all trained on a large corpus of information from the internet at large, and then things like Copilot are trained specifically on code from GitHub. But in the last couple of years, we've moved on more to what we refer to as these conversational large language models. So the conversational large language models are things like your ChatGPT, your at the time the slide was made, it was Google Bard, now it's Google Gemini, Mistral, all of these different models that are made to kind of simulate human conversation. So rather than it trying to complete my prompt, I give it a complete thought, I give it a complete prompt, and it responds with what it most likely thinks I want in response to that. And then I can respond back, and it formulates this conversation that anyone who's used ChatGPT is all too aware of at this point. So how do these large language models work? Right, we're discussing using them to write things. How do they actually function behind the scenes? We start, ultimately, they are trained over large data sets of text to quote unquote learn and then predict whatever the next token is or whatever the next thought is. You'll see GPT come up a lot. Obviously, ChatGPT is the big one that most people continuously talk about. GPT stands for Generative Pre-trained Transformer. So generative just meaning that it generates new response for you. Pre-trained is that it's not actually dynamically learning. That's a question we get a lot when discussing this is, well, is it actually learning more just from you prompting it? And the answer is not quite. Ultimately, a lot of our prompts, because OpenAI has permission to do this, or any of these large language model designers have usually want permission to do this. They'll take your prompts and eventually incorporate that into the data set and into the training, but it's not learning as it goes necessarily. And a transformer model is just a type of machine learning model or a type of AI model made to help us take in this large corpus of text for training. It allows us to do things like train over large language, as it were. Uh, they can be fine-tuned for specific tasks, and that's a lot of what we've seen going on with things like GitHub Copilot or CodeLlama or all these coding-specific large language models. Is they're originally trained on something like the Common Crawl and Wikipedia and just general information from across the internet writ large. They're originally trained on that, and it gets some information so it can recite the first law of robotics or what have you. And then when you want it to do a specific task, you fine tune it over a specific data set, like in the case of GitHub Copilot, it was trained over all of the code on GitHub. So in terms of how these actually produce information, I mentioned tokens on the last slide. A token is generally about 3 to 4 characters. It's not a fixed value. According to OpenAI, it's 3 to 4 characters or 3/4 of a word. It's a vague definition to just give you some idea of what it's processing. But essentially, a token is just a unit of processing for a large language model. So you can see here, if we prompt with int main open parenthesis int, each of those being a token, it's going to try to predict whatever the next most likely token is on the output. So in this case, 92% chance we're looking for argc because we're writing this main function. So that's what it's going to try to return to us. So how do we actually generate hardware with this? What does that look like? To start with, there have been a handful of fine-tuned Verilog-specific large language models over the last several years. It really started with this one called DAVE, which stands for Deriving Automatically Verilog from English. Probably my favorite name for a paper I've ever read. But it was a fine-tuned GPT-2 model trained specifically over a bunch of textbook problems. And this came out of my group here at NYU, or the group I work for here at NYU, a little bit before I joined, primarily made by Dr. Hammond Pierce and Dr. Ben Tan. They fine-tuned a GPT-2 model, which at this point is very out of date, over a number of textbook problems, and found that they could get it to generate syntactically correct, functionally correct in many cases, Verilog. However, it was severely limited by the amount of training data they had and the size and functionality of GPT-2 at the time. They found it was really good at maintaining correct Verilog syntax, but any question that involved any sort of quote unquote creativity where new variable names would have to be made or complex processes would have to be made, they found it failed pretty readily across the board with anything more complex than, the most basic type of questions you would ask a freshman digital logic student. Following up on that, a few years later, we came up with Verigen, and Verigen was fine-tuned over a codex model, which is codex was OpenAI's code-specific model from GPT-3. So it was the next generation of their GPT model, and then specifically it was already fine-tuned to write code. We then further fine-tuned it to write Verilog specifically. So rather than only training it over a textbook, we trained it over all of the Verilog that could possibly be scraped off of GitHub, as well as a bunch of textbook problems from multiple textbooks, I think several hundred, although I don't remember the exact numbers. And it was shown to, in terms of Verilog specifically, outperform the state-of-the-art, more general models at the time. GPT-3, ChatGPT 3.5 is really what it was going toe-to-toe with, and actually it was a little bit better than ChatGPT when ChatGPT originally released sometime late 2022. Verilog eval is that was late 2023. This is a more recent thing, but it's a fine-tuned code. But they, along with a data set of benchmarking problems, they released a fine-tuned code gen model. Code gen being another specifically code generating large language model. And then RTL Coder is the newest one that we've seen come out, which has a couple of versions, one fine-tuned over a Mistral model and one a DeepSeek model. The specifics of what models things are fine-tuned over really comes down to how large you want the model to be. Do you want it to be cost effective? How many parameters, things like that. But ultimately, this just goes to show there's a lot of interest in making these models specifically for Verilog. My interest is actually kind of the opposite of that. I find it far more interesting to look at these commercially available models, the ones that are not trained specifically to write Verilog, and see, well, how can we work with them to get them to generate the best Verilog possible? I look at this primarily from the standpoint of someone who ChatGPT came out and I was told, hey, figure out how to do something with it. I didn't have the ability at the time to fine tune anything. So I said, okay, let's see how good we can get it without doing any additional training, because training takes time and costs money and it's a complicated process. So the original work on this was something called Chip Chat. This was published in MLCAD last year. And we looked at using human feedback in a conversation, because we were looking at all these conversational models, to design something unique. And our goal here was to see how complex of a design could we make. We also were targeting not just making a complex design, but also targeting actually taping out the design on something called Tiny Tape Out, which is a program run by Zero to ASIC, run by a fantastic guy named Matt Venn. And with Tiny Tape Out 3, we saw an opportunity to tape out the first fully AI written design. And by and large, we succeeded at doing that. So the idea here was, let's make a basic processor. We only had 1,000 standard cells. We only had 8 inputs and 8 outputs, in the inputs including the clock and reset. So it was a heavily constrained design. And we pretty much said, let's build a microprocessor. We want it to be an accumulator-based 8-bit architecture, no multi-byte instructions, because we only have the 8-bit inputs. How should we begin? And we ended up with these 18 conversations, all with ChatGPT 4. At the time we were doing this, ChatGPT 4 had just come out, so there were some rate limiting issues, and it was a little bit of a headache at times. But we got, generally speaking, very good results. So each of these conversations is an actual separate conversation in ChatGPT. If you go to the sidebar there, you can see each of your old conversations, with the exception of the ones that are connected with these red arrows, where a conversation was continued when we did something like found a bug or identified a place where an improvement needed to be made for it to be properly functional. So the first conversation, of course, starts with the specification. It's still the same digital design pipeline. We're just simplifying it. We start with specification. We're defining an ISA. And then we get into actually getting the LLM to write the Verilog, with defining the register, defining shift registers in memory, all of this planning, all the way up through making an actual Python assembler for this fully custom ISA. Once we had a Python assembler, we could test it, and testing it revealed all of these issues that we missed in the immediate process. So then that's where we start going back and saying, okay, conversation 10 is actually a conversation, an extension of conversation 0. Excuse me for one moment. Conversation 10 is just an extension of conversation 0, where we need to update the way we're doing branching, because the way it was originally specified, we didn't catch it at the time, but we essentially couldn't actually loop properly. We couldn't create subroutines. It became a whole issue. A bunch of changes needed to be made for that, et cetera, et cetera. Ultimately, we ended up with a functioning processor. And looking at the amount of quote unquote effort that it took us, it was pretty minimal. We prompted the LLM to do something 125 times. That's not a whole lot. All things considered, not a whole lot. We did have to get it to restart a number of times. If a conversation ever got to a point where it was producing something that was very clearly wrong, we would just ask it to regenerate what had been an issue. So we did have these restarts and whatnot, but ultimately we saw that the user only had to write just shy of 2,000 lines of code, we'll call it. The LLM generated about 5,000 lines of mostly Verilog and then a little bit of Python for the sake of making that assembler. And we ended up with a functional processor with absolutely none of the Verilog itself written by the user. It was entirely English, plain language, natural language prompting. Just a very brief look at what the processor, the kind of looks like. This is the data path. It's an accumulator-based architecture. It is very simple. It is nothing incredibly complicated. We didn't get it to generate a RISC-V core or anything, but we showed that we were able to, using only natural language, get a functioning design in Verilog on the other side. Some interesting things to note about this is it did fit on tiny tape out. It was successfully taped out. I don't have the board in front of me, unfortunately, but I do actually have a board that runs this design, which is really cool. And we've been claiming for well over a year now that this is the first fully AI generated tape out, and no one has disputed it yet, so we're just going to keep claiming it. So what at this point we have is this thing that we call chip chat, talking with the LLMs to generate all of the Verilog. There are some concerns about the practicality of this, how well this scales up to a significantly large design if you're trying to make a RISC-V processor. It gets a little touch and go there at points. We've certainly tried. It is tough and leads to some problems. A lot of hardware design relies on things like third-party IPs and third-party models. You have to either train the model on that or provide it as context, which becomes a bit of an issue. Especially, there are copyright constraints with that, but it also becomes an issue with just what the LLM can process. There's the human component. We had, relatively experienced hardware designers working on this. We could not give the same problem to a freshman or someone who didn't know anything about Verilog at all and get them to accomplish the same thing. There's still domain-specific knowledge that needs to be used for this. And then correctness. Evaluating correctness is tricky. You still need things like Verilog test benches, which leads a little bit into the next work we did, which is trying to evaluate the LLMs in a bit of a more rigorous way. We structured a conversation flow where we asked for both a design and a test bench to test that design. So we started with this initial LLM prompt, and that initial prompt would be something like, we gave it ultimately 8 benchmarks, all based on what we ask students in the undergraduate digital logic class here to do. It started with a shift register and a sequence detector, and we essentially said, I'm trying to make we'll say shift register in Verilog. These are the inputs, these are the outputs. Can you write this for me? The first thing we did was a litmus test to just see, could it even get the IO correct? We found there were a bunch of models at the time we were doing this where we couldn't, so they were just kind of a non-starter. We'd loop on that a little bit, but if they couldn't even generate correct IO, we just called that done. It's not very well shown in the flowchart here, but the next thing we asked for was, can you make a test bench for the design that you just made? And it would generate that, and then we would throw it into Icarus Verilog, which, for those who aren't aware, is an open source Verilog compiler and simulator. Coming out of that, if we had errors, we would start feeding those back into the tool. If we didn't have errors and everything passed, we'd call it a success. And there's a bit more to that I'll get to in a moment. I need to speed up a little bit here. I'm looking at my time. We would feed that information back into the LLM, first just giving it the tool feedback. And if it kept failing at that, we would slowly incorporate more and more feedback from an experienced hardware designer to kind of guide it in the right direction. And if it still couldn't do it after being told pretty explicitly what was going wrong, we would just call that a failure. Too many problems. We're going to give up on that. So what the results actually looked like, at this time we were trying both ChatGPT 3.5 and ChatGPT 4. We found that ChatGPT 3.5, regardless of the amount of effort you would put into it, I should point out, we also set a depth on those iterations of 25. At the time we were doing this experiment, ChatGPT 4 had a rate limit of 25 messages per 3 hours. So we pretty much said, if it can't complete the conversation in one 3-hour chunk, we're going to call that a failure. So that was our other failure case. So ChatGPT 3.5, we saw a lot of cases where it couldn't make a functioning design in those 25 messages, or it couldn't make a functioning design after even getting very explicit human feedback. ChatGPT 4, on the other hand, we still saw failures for sure, but we saw far fewer failures. We saw a lot more results in fewer messages. So our first shift register was completely correct, or at least it passed its own test bench in only 3 messages, only a little bit of feedback using only tool feedback, whereas with GPT 3.5, it only created one successful one out of our 3 test cases, and it still took 13 messages. It was a lot of effort to get there. And we see, that general trend continuing from GPT-4 and GPT 3.5. GPT-4 was able to pass the majority of the tests using only tool feedback. There is this interesting middle column here where we say if a design is compliant or not. One of the issues we found with asking the large language model to create its own test bench is that large language models have no concept of test coverage. So they would create a test bench and it would pass a test bench, and the test bench would not actually validate the design in any way. So we see that specifically, my favorite example of it is the dice roller here in test case 1, where we asked it to simulate a dice roller. The test bench it generated just checked, is the output between 1 and the number of sides on the die face, which it always was, because the dice roller always rolled a 1. So the test bench passed. It wasn't actually a compliant design because it's proper test coverage. So the feedback we got on that work was largely, well, the human feedback portion of it is still kind of nebulous. So we asked, it's nebulous, it's costly. Can we remove human feedback? Or at the very least reduce it? And that leads to the question, can the large language models understand the feedback from the tools if the test benches are explicit enough? So we're going to remove the problem we ran into with non-compliant test benches from the last work. We're going to use a set of standard benchmarks with known good test benches, and we're going to see, do these work? So this is something we've termed AutoChip. We are automatically generating the chip. We get our design prompt from that set of benchmarks, throw it through a large language model. We get Verilog on the output, and that's more or less the same. If we have compilation errors, we feed that back. If we have simulation errors, we feed it back whatever the test bench reports went wrong. To benchmark this, we used a website called HDLBits, which is a website for teaching Verilog. It's by and large relatively simple problems, but it gave us a lot more of them across numerous different types of problems. We ultimately tested this on 120 different prompts from this website and test benches that the website uses. Ultimately, we saw some pretty fantastic success. A brief note on the type of feedback, going back to our discussion about tokens, large language models have limits to how much information they can process. We refer to them as token limits because they are limited by the number of tokens. Full feedback meant we weren't trimming the conversation at all, so it would just grow and grow and grow and grow. We saw pretty often that would violate token limits, and in the cases where it didn't, it would just lead to not as good results. We found that if we only provided the most recent information that needed to be fixed, we saw by and large better results. So we see our best results came from ensembling GPT 3.5 with GPT-4. We would get to a certain point, and that's what this multiplexer here is made to represent. We get to a certain number of iterations of GPT 3.5. If it still wasn't passing, we'd hand it off to its big brother GPT-4, and GPT-4 would usually get it across the finish line. And we saw up to 87.15% test cases passing on average. We had a lot of things that passed completely. There were still a number of things that never really quite succeeded. And we break that down by category here. HDLBits breaks up their designs by category. We evaluate on that same metric. So we essentially see basic circuits with GPT 3.5. A lot of these things, the getting started questions pass very well. The basics pass very well. And then the more complicated things like writing test benches, we see we were never really able to succeed at properly because, again, no real concept of test case coverage. There were a few other things that we saw were interesting. GPT 3.5 was not phenomenal regardless of the amount of feedback at sequential logic, whereas adding even a single iteration of GPT-4 managed to fix a lot of those problems. Still not perfect, but certainly an improvement. And that's where we're at the moment. We're continuing the work on AutoChip. We actually just submitted a paper with an updated version of things, which I would love to have been able to share with you today, but unfortunately, like I said, just submitted. Basic conclusions. Large language models we've been able to show are very good at helping to design hardware, but still struggle significantly to make it on their own. human feedback drastically improved our results over automated feedback. But by implementing things like ensembling and that feedback loop, we were able to get much closer to properly functional designs. Ultimately, the initial prompts still require a lot of domain-specific knowledge, so you still kind of need hardware engineers working on it. But it gets a lot closer and it lowers the bar for that design. Uh, Someone who has just learned Verilog can get a lot closer to designing more complicated things than they could before. There's still very much an open question on how best to prompt these large language models to get those best results. We took a very rudimentary approach of taking HDL bits and giving those as prompts and then using tool feedback. But there's a lot in the way of prompt engineering we can look at. And we see that, using that feedback, even just tool feedback, can ultimately lead to much better results, with much less effort. I've got a slide of references for all the papers that I mentioned throughout this. And I'd like to thank NYU Center for Cybersecurity. Dr. Ramesh Kari is my advisor. I have also worked extensively with Dr. Siddharth Garg, and then Hammond Pierce, Benjamin Tan, and Shaljit Thakur are all former postdocs who have all gone on to do bigger and better things elsewhere. But they've all been very much involved in this work and very instrumental in helping with it. So thank you guys all very much, and I'd be happy to take any questions.
Thank you, Jason. People use the Q&A tool, and I'm also going to pop up a poll here. So if we just give Jason some feedback. But questions from the audience. I know Neil might have a few, but before we even get there, how do you know that the tool even starts in the right direction? Have you, launched something and it's gone like 180 degrees in the wrong direction?
Yep. Yeah, that happens a lot. Ultimately, that's one of the things that benefits from a person being in the loop, is being able to evaluate, is this completely off the rails? But also, like I said, we just submitted an updated version of AutoChip that kind of seeks to answer that a little bit. A very brief overview of what that looks like. We actually generate multiple candidates per iteration, and then we rank them based on how well they're passing the test benches or the compilation. And if we have something that passes 80% of the test cases off the bat, we know that it's better to follow that than the thing that couldn't even compile.
Makes sense.
Yeah, it's a very notable result we've seen in all of this work has been the initial couple of iterations, regardless of what you're doing, sets the tone for the rest of the design. So if it's hallucinating badly at the start, you're unlikely to get something that works. All right, I'm gonna move the panelist view onto. Actually, no, I'm not. Never mind. Next question.
Yeah, Jason. I actually had a question myself. Do you
Sure.
see the point? You see test bench, they don't have the concept of test. Do you think we could get to the point where we'd have a model trained specifically to generate test benches, then we could incorporate that in your kind of auto chip flow?
Absolutely, yeah. That's not something that I've been largely working on, but everyone we've talked to about this has pretty much gone, well, that's great, but I don't want to write test benches, so can this do it? There are a couple of people in my group that I know are working on that, at least to some extent. I have not been super involved in that side of things. It's a notably more challenging prospect. I will say there's also been work done by a joint effort between us at NYU and a group down at Texas A&M on writing assertions with large language models. It's primarily focused on security assertions, but they work for verification as well. So that work has already been largely undertaken. And then looking at, rudimentary Verilog test benches are just, test benches as we usually write them. There's been some work on that, but it's difficult to give a large language model kind of this sense of an understanding of what it's writing. Going back to how they work, they're just trying to predict what you want them to say, essentially. They're just trying to predict, based on everything I've seen before, what's the most likely response to this question. And unfortunately, the most likely response doesn't necessarily understand what you've made. If you have a creative design with unique test cases, it's hard to get it to understand what those test cases are because it's not doing any of this processing in the background. So we've discussed ways of using AutoChip to improve that, but it's still very rudimentary work at the moment.
Okay, thank you. We got a question from the audience. How optimistic you about the future potential of automating chip design verification with LLMs, and kind of where do you think we'll be in 5 to 10 years?
How optimistic I am is a much easier question to answer. I'm pretty optimistic. I don't think, my worry is not that hardware designers are ever going to be replaced. I've gotten that question more than a few times as well. I really see this as something that just lowers the bar. So for weird, complicated designs, I think by and large, we're still going to need hardware designers for the foreseeable future. But this does help take care of a lot of the easier boilerplate stuff like weird glue logic. It's good at handling things like that. As far as where I see us in the next 5 to 10 years, I couldn't begin to tell you. I didn't know what a large language model was a year and a half ago or 2 years ago. A lot of this AI portion of research moves so quickly. If you think about, Dave, that original paper on fine-tuned Verilog, on a language model fine-tuned for Verilog, it was fine-tuned over GPT-2, and its results today would be astoundingly terrible. And that was 4 years ago.
Right.
2 years ago, ChatGPT 3.5 came out, not even quite 2 years ago. And ChatGPT 3.5 is in part getting deprecated because it's just not up to snuff anymore. Where we're going to be in 5 or 10 years, I'm a little terrified to think about it, truthfully.
Yeah, I guess do you see in that 5 to 10 years us continuing down kind of the one model to kind of do everything, or more into a lot smaller models, more targeted, and kind of that ensemble approach of
Definitely the latter. So already we're seeing a lot of what are called mixture of experts models. No one's really 100% sure, at least OpenAI won't tell us exactly what GPT-4 is doing in the back end, but there's a lot of supposition that it's a mixture of experts model where it's a lot of different models trained on their own information, and then an overarching thing that kind of figures out what model to query at what percentage. So I think we're going to see more and more of that, partially for computational feasibility and partially just it seems to result in better results. Seems to give better results. But also, I wouldn't be surprised if even like in the open source community or the hardware design community, we end up with this collection of models where one is good at making sequential designs and one is good at making glue logic and one is good at making assertions. And ultimately, we just create tools that combine all of them in creative ways. I think that's probably where we're headed most likely.
Okay, thank you. We had another question from the audience. Is design for testability considered in this design, or is it just kind of a pure functionality?
At the moment, it's really just pure functionality. Truthfully, I haven't even really considered specifying design for testability sorts of things. We're also, at something that we are quite literally just starting to look at. I've got a meeting about it tomorrow. Is looking at the way that we're prompting these things and are the current benchmarks we're using really up to snuff. HDL bits, as good as it is because it provides us this large set of benchmarking problems, is also still pretty limited in how complicated of a problem it asks. No hardware designer in industry is doing the problems that they ask in HDL bits. So we need to start looking at, how are we actually doing hardware design, and can we start making benchmarks specific for that? And that's, it's something we've been discussing for a while, but I think at the very least, my group's going to start moving on that a little bit more.
Sure. I guess we still got time. Have you had any success with kind of larger designs with multiple components?
With hierarchical designs, it is definitely a bit more complicated. We've had some success, but not with automating it. So I've got we have a couple of research summer research interns from NYU Abu Dhabi who have recently been working on trying to make I think a RISC-V pipeline exclusively using ChatGPT, and there's at the moment no hope of automating it, but through knowing how hardware works, through good feedback prompts from a hardware designer, we've been able to get pretty close, if not there. I need to figure out where they're at the moment, but it's certainly getting there. I don't know when it'll be automated, but we're working on it.
Excellent. Thank you.
Okay. Thank you, Jason, for an excellent presentation.
Absolutely. Thank you.
I would like to thank our sponsors once again, ASC and Amcor. And with that, I will wish everybody a great rest of their day and look forward to seeing you at a future MEPTEC event. Thank you for joining us.